Okay, let's take a look at this problem. So we have a block of ice with a certain mass slides down an inclined plane at a given angle. And, we're told that it starts out from rest, and we want to know how fast it's going once it reaches the bottom. So first we'll draw a picture of what's going on here. Um, here's our ramp like this. And then I'll just call this angle theta instead of writing in the 36.9 degrees. So this is theta here. And we have a block. Let me give a different color to the block here. Block of ice. It slides down. This ramp is 7.5 meters long. So it's like this. This is 7.5 meters. And it starts out at rest at the top. I'll just call the top like point 1 up here. So this is maybe position 1. It's like an initial position. And then this is position 2. It's like our final position. So the block is going to start up here at 1 and then move down here to 2. Okay, so we want to know how fast it's going here. So this is very similar to some previous problems we've done where we can just use Newton's laws and kinematics. So let's actually run through a couple different methods here. So we'll say method 1, our old method. This is Newton's laws and kinematics. So to do this, the first thing we need to do is we need to establish a coordinate system, right? And what we've done for problems like this in the past is we said that we have a coordinate system which is, parallel and perpendicular to the incline, right? So positive x going down the incline, positive y going out of the incline. And then we would start with a free body diagram of this. So free body diagram of the block. So that's what we're interested in, how that's traveling. And the free body diagram will look something like we have an mg sine theta here. We have a normal force here. And we have an mg cosine theta here. And if we had friction, which it actually says over here, it says that we can ignore friction. So if we had friction, then we could have drawn friction back this way, right? But we don't actually have any friction, so it makes it a little bit simpler to deal with here. So there's a free body diagram of the block. After a free body diagram of the block, then we can say, all right, so summing the forces. Well, I'm really mostly interested just in the x direction, right? Since I don't have any friction, I'm actually not going to need the normal force. So I can just sum the forces, and the x direction equals mass times acceleration and the x direction. So we have here mg sine theta is equal to max. Of course, this mass cancels out on both sides, and we're left with our acceleration, and the x direction is equal to just g sine theta. Okay, and then now that we have this acceleration, we can use kinematics, right? So there's our Newton's laws portion to give our acceleration, and then to find out how fast it's going once it gets to the bottom, we'll use kinematics. This is like from point 1 to point 2. From our initial to final. And so we knew here, when we're using the kinematics, we extract some of the given information first, right? So we know that V1 is equal to 0. We know that delta x is equal to 7.5 meters. So it slides 7.5 meters down that incline. And we also know that the acceleration and the x direction is equal to g sine theta, right? And we want to find v2. or V final, right? So then we can use that third kinematic equation here. We can say V2 squared is equal to V1 squared plus 2ax delta x. And so then V2 is equal to plus or minus V1 squared plus 2ax delta x. And so then just plugging stuff in here, and actually with it starting out at rest, that was very nice. V1 is equal to 0, right? And so plug it in from here, we'll get V2 is equal to plus or minus the square root of 2, and acceleration was g sine theta, right? So 2g sine theta times 7.5. This is what we end up with for V2, which plugging it in, this comes out to 9.39 meters per second. And so this is one method, and then I just want to show that we'll get the same exact result using energy analysis, because after all, this is the energy chapter. So that's how we can do it with Newton's laws and kinematics. All right, now method 2, energy. So with energy analysis here, that's conservation of energy, or the work energy theorem, or really, conservation of energy comes from this work energy theorem. So I'm going to redraw it here. I'm going to redraw the problem. And for energy analysis, and I should add these points 1.2. For energy analysis, the coordinate system isn't as important, really. But what we choose to be our datum is very important. So choosing the datum is sort of like choosing the coordinate system here. And I want to choose a point, the datum is where the height is equal to 0. I would like to set my height equal to 0 at a point where it is going to be very convenient for calculations. I just want to simplify calculations as much as possible. I can really choose the datum anywhere I want, but easiest if I choose it, maybe my height equals 0 to right here, right? So I'll call this the height. Really, this is, like the height at point 2 is equal to 0, right? So this is my datum right here at the bottom of the incline. And then some other information I know that V1 is equal to 0 here, right? And so since there's no friction, then I know that I'll just say since there's no friction, the coefficient of kinetic friction is 0. This is the way I was saying it's frictionless. Since there's no friction here, then we have the mechanical energy at point 1 must be equal to the mechanical energy at point 2. Okay? And by the way, we had this was 7.5 meters, right? Okay, so mechanical energy at 1 equals mechanical energy at 2. So by cleverly picking these points, point 1 was where there was no speed, right? So there's also no kinetic energy, right? So, well, let me actually write out all of these. So we had the kinetic energy at 1 plus the potential energy at 1, which is just gravitational because there's no springs here, is equal to the kinetic energy at 2 plus the potential energy at 2. But by cleverly picking these points, point 1 was where it hadn't started moving yet, so it had no kinetic energy. And I set my datum at point 2, so I just said, well, there's no potential energy at point 2. Then what we're left with is just the potential energy at 1 is equal to the kinetic energy at 2, which is just saying that all the energy at the top of that ramp is converted to kinetic energy. All the potential energy at the top of it is converted to kinetic energy at the bottom. This is essentially what this says here. And so then this is mgh1 is equal to 1/2 mv2 squared. And the mass cancels out. They gave us the mass of this, but we didn't end up needing it anyway. In either case, Newton's laws in kinematics or with the energy analysis. And so we end up here with V2 is going to be equal to the square root of 2g h1. Now this h1 though, this is the height of point 1, right, from the datum. So h1 is not the 7.5 meters. It is this height, just a straight up vertical height right here. This is h1. Not along. I see a lot of common mistakes that people will say that it's along here, so 7.5 meters. It's not that. It's just this height right here. So we need a little bit of trig to find out what h1 is. And so with the hypotenuse of 7.5 and the angle theta, h1 is 7.5 sine theta, right? So we have h1. This is 7.5 sine theta. And so then, and actually this V2 should have been a plus or minus, right? So then V2 is going to be plus or minus 2g times 7.5 sine of theta. Which, if you go back and look, so this is what we got from energy analysis. If you go back and look at what we got with Newton's laws, it's 2g times 7.5 sine theta. I wrote these, the order is different a little bit, but it's 15g sine theta, right? And so that's exactly the same thing as this one. It's 2 times 7.5, 15g times sine of theta. And so this is equal to, same thing that we got up above, this 9.39 meters per second. So either way works. Newton's laws in kinematics or energy analysis. And unless I state otherwise, you can use either, or I encourage you to use both on a problem like this, where you can use Newton's laws in kinematics or energy analysis. With a spring, though, you have to use, either have to use calculus or you have to use energy analysis if I had springs involved. We didn't have any springs involved, so we could have done either way, but just kind of just a heads up there.